Welcome back. This is chapter 11. This will be the first chapter of your module 3, and we will only consider the section 11.1. So we're going to talk about the catabolism and energy release and conservation and the different types of microbes that are using this. So we're going to talk about the carbon energy and the electron sources of different types of energy requirements, different bacteria, and we are going to look at the products of the Fluidic reactions and discuss about a little bit about the metabolic flexibility of these microorganisms. So for each organism to survive, they need to have a source from where the energy comes, which will fuel the synthesis of the organic molecules. So for satisfying together these requirements, we need to have a carbon source, often provides the hydrogen. Now this, when it provides that hydrogen H or electrons, this is most of the time is an organic molecule. So if there's an organic molecule, say for example, just giving a straight, if there's an organic molecule that we are ingesting, which does have a glucose, that glucose will provide us energy, which will contain hydrogen, oxygen, and the electrons. But there are many different bacteria which do not have access to the glucose or cannot use that. For them, the carbon source could be just carbon dioxide, or it could be something else like a complex material. And from them, they can extract that electrons, hydrogen, and oxygen, all of these requirements to make the molecules usable for the energy production by the reaction of a chemical, or from which will be an electron donor, or from a source which is light. So let's dissect this problem. So the heterotrophs use the organic molecules as a carbon source, which often also serve as an energy source. This is a classic example of us. And we can also use a variety of carbon source. So all our food that we take they are organic molecules, and they often serve as an energy source. So the same thing with the bacteria, they can also use these organic molecules. We can just think about that. It could be the carbohydrates, it could be the proteins, it could be the lipids or the nucleic acid. They can take them up, they can break it down, and they can synthesize new molecules out of them. So both carbon source and energy source for the heterotrophs are the same. So on the other hand, if they are autotrophs, they use the carbon dioxide. See that this is an unreduced carbon dioxide, means that there is no hydrogen in there. So this is their sole principle of the carbon source. To reduce the carbon dioxide, if they're using that, they need something different, which is providing the energy to reduce the carbon dioxide to a molecule like a carbohydrate, and they need the power of light, or sometimes they also need the power of a chemical reaction. We are going to see that to reduce the carbon dioxide into an organic molecule. And must obtain energy from other sources means that these autotrophs cannot use the organic molecules as the energy source, and must obtain energy source that we just talked about, just from a chemical reaction or from light source. So let's take a look at this. So based on the energy source, the phototrophs use the light, and the chemotrophs obtain the energy from the oxidation of the chemical compound. And when one chemical is oxidized, it will reduce the other, and what is called as a fixation of that molecule. So when we use the word that carbon dioxide fixation, what we mean by that the carbon dioxide is reduced in the form that we have introduced hydrogens in there, electrons in there, and we have reduced that chemical, which can be used as an energy source, because we have already put that energy into that molecule that is being synthesized from the carbon dioxide, and that can be used as a food fuel for everything. Another important thing is that based on the electron source, so the lithotrophs use the reduced inorganic substance. On the other hand, the organotrophs obtain electrons from organic compounds. So where is that electron source that is needed for the energy source? So if there are reduced organic substance, remember that this word is important. Reduced means that these inorganic substances already does have electrons in them in the form of hydrogen most of the time. So when these inorganic substances are oxidized, which is the opposite of the reduction, they will obtain those electrons to do their own synthesis of the molecules. So the energy is being transferred from the reduced inorganic substance to their own reduced material, whereas the inorganic substance will get oxidized as they are losing the electron. On the other hand, the organotrophs obtain the electrons from organic compounds, means one organic compound which is already also in the reduced form is going to deliver the electrons to another material which is the organotrophs are fixing or reducing, whereas this organic compound from where the electrons are obtained are going to be oxidized. So this is the overall principle of the nutritional types of the microorganism. So let's take a look at these major nutritional types, and this is the main part of this small chapter section. So the photolithotrophs, as it says, the photo means light, litho rocks, auto means they can make their own food or the energy source by themselves. That's why they are autotrophs. So let's take a look at where they get the carbon source. So the carbon source is carbon dioxide, atmospheric carbon dioxide. Energy source is light, and the inorganic electron donor. So using these combinations, what they do that by the energy source of the power of the light, these inorganic reduced material is going to get oxidized, and these inorganic materials oxidation will fuel the fixation of CO2. So there will be introduction of these hydrogens into this so that this will be reduced, this will be oxidized. So electrons is flowing from this material to this, and that's how they make their own molecules for the energy production. Example is the purple and green sulfur bacteria, cyanobacteria, diatoms, and these are essential for the biogeochemical cycles that goes on the earth, and the sustainability of earth actually depends a huge amount on these different types of energy requirement. Photolithotrophs, very important. Photoorganoheterotrophs, on the other hand, the carbon source is organic carbon. As soon as we look at this, like take a look at this, that they need light energy. Organoheterotrophs, organo means that they need the organic material, which is already preformed by some autotrophs. And heterotrophs means that they need these preformed organic molecules from somewhere else, and it could be different sources, but as they are not auto, they cannot synthesize their own material. So they're using organic carbon with the help of light. Organic E-donor means these are preformed molecules in the form of carbohydrates or proteins or others. And with the help of the light, they oxidize these, which will provide them the energy. This is a very specific group where you see this purple non-sulfur bacteria, green non-sulfur bacteria. These are mainly present in some of the polluted lakes or the rivers, and you do not have too many of example of these organoheterotrophs, but there are some example of these, as I said, in high organic content material containing lakes, rivers can have these photoorganoheterotrophs. Chemolithotrophs, on the other hand, the carbon source are carbon dioxide, and the energy source is inorganic chemicals, and it's an inorganic E-donor. And as the word says, that the chemical inorganic material is going to supply the electrons. Litho means it's rock, and they can synthesize their own food. So what they do, that they use the atmospheric carbon dioxide, but they use the inorganic electrons to fix that carbon. Again, these are different types of reduced inorganic material which become oxidized exactly like this, photolithotrophs. The inorganic reduced material get oxidized, and the electrons flows into here to fix this carbon dioxide. So sulfur oxidizing bacteria, see that we use the word oxidizing. Sulfur oxidizing bacteria, hydrogen oxidizing bacteria, methanogens nitrifying bacteria, iron oxidizing bacteria. Let's take just one example. Say, think about ammonia. So ammonia is NH3, which is the reduced form. When you have a nitrifying bacteria, this hydrogens from there is going to convert into something else for fixing the CO2. The hydrogen will come over here. And as the NH3 or the ammonia is getting oxidized, it can form into nitrate, say NO3 or NO2. Iron oxidizing bacteria, so from iron, it can get iron oxide. Sulfur oxidizing bacteria can make from sulfide to sulfate. So sulfide to sulfate, ammonia to nitrate, iron to iron oxide. These are all different types of ways that the chemolithotrophs or to get the electrons to be fixed into their carbon dioxide to reduce this to form food. Chemolithoheterotrophs, on the other hand, the organic carbon source that we saw that already, heterotrophs, energy sources inorganic chemicals and inorganic e-donor. Some sulfur oxidizing bacteria, which the reduced form of the sulfur, they oxidized into sulfate, and that energy is used to break down organic carbon to synthesize new organic molecules. So they are already using organic molecules, but they use the power of inorganic source of electron to convert them to something else. So here, they are not synthesizing their own molecule. They are obtaining the organic carbon from a preformed source, from another inorganic source, which has been done by some other autotrophs. And they're using this, the power of the inorganic electron, to convert them to a different molecule. And then you have a chemoorganoheterotrophs. They use also the organic carbon, organic chemicals, often same as the carbon source. And you have the organic electron donor, often the same as the carbon source. So these are most non-photosynthetic microbes, including most pathogen fungi, many protists, and the archaea. So what we mean by this organic carbon, that these are the most of the organism which can use the preformed, say, carbohydrates or proteins or lipids or the nucleic acid. They will get all of these reduced organic carbon into them, and they will break it down again. As they are breaking it down, that will be the electron donor. That will be the energy source. And as they are breaking down, that will be the carbon source. And after breaking down, using this energy, they are going to form new organic carbon. This is exactly what we do as well. So if we just get just a very simple, straight example. So table sugar sucrose is made up of two different monosaccharides. One is a glucose and another is a fructose. So there could be some bacteria which can take up the sucrose as well, and they will break the sucrose down into glucose and a fructose, and they can get those electrons from the fructose as well as glucose, and they will fuel the glycolysis, Krebs cycle, and the electron transport chain. And the power of ATP will be used to make more of these organic carbon, which is also the same source. So this is the overall procedure. Let's take a look at a little bit different way that how it happens, that despite the diversity of energy, electron, and carbon sources used by organism, they all have some of the basic needs. What you need the ATP as the energy currency, wherever it is from. They need the reducing power to supply electrons for the chemical reaction, as we just discussed, and they need the precursor metabolite for the biosynthesis. And let's take a look that for each one of them, how these different organisms use them for their purposes. So if we are looking at the energy source, the chemoorganoheterotrophs, as we say that organo and heterotrophs, or chemoorganotrophs use the organic molecules which are already preformed by some autotrophs. Chemolithotrophs use inorganic molecule for their energy source, whereas the phototroph use the light for their energy source. So organic molecule means that there is already the energy is inside those organic molecules. As that organic molecule is being broken down, the energy is released to form the ATP. For the inorganic molecule, when these inorganic molecules which are in the reduced form is oxidized, that releases the energy that is used for making the ATP, whereas the phototrophs use the light source to produce the ATPs. On the other hand, what is the carbon source? For the autotrophs, that is the carbon dioxide, so which is reduced or fixed to produce the precursor metabolites, whereas the heterotrophs, and you can name them chemoorganoheterotrophs, chemolithoheterotrophs, and those use the organic molecules which are preformed by the autotrophs already, and they are the precursor molecules to produce their own material. And the last part is the electron source. The organotroph use the organic molecule and the reducing power of the electrons, which comes from organic molecules which are preformed by some autotrophs, whereas the lithotrophs use the chemicals which are inorganic molecules, and these inorganic molecules they use is in the reduced form. So these lithotrophs oxidize these reduced inorganic molecules, and as they oxidize these molecules, the reducing power or the electrons come out, and those are used to produce their metabolites and building block or making their monomers to macromolecules. So this is the overall process that how the fueling reactions are used by these different types of major nutritional types. So that is the only material that we are going to cover in this chapter. That's all for your section 11.1.